Adaptive radiotherapy relies on repeated imaging to track anatomical changes during treatment. But accurate dose calculation requires CT-calibrated electron density, and we don't always want to expose patients to another diagnostic scan. That's where synthetic CT generation comes in. The standard approach treats this as a direct regression problem. Map MRI or CBCT voxels straight to Hounsfield units. But CT intensity distributions are notoriously brutal. You're looking at a range from -1,000 to 3,000 HU, with a heavily skewed, long-tailed distribution. When a network tries to learn this globally, it gets dominated by the abundant soft tissue voxels, and the sparse but clinically critical structures like lung parenchyma or cortical bone get averaged out into noise. What if we stopped fighting the physics of CT imaging and instead used it as a prior? Radiologists don't view CTs as a single monolithic intensity map. They switch between clinical windows to isolate specific anatomical regimes. Lung windows, soft tissue windows, bone windows. Each window normalizes a specific intensity band, flattening the distribution and making the underlying structures far easier to learn. We applied this exact intuition to deep learning and built Wing, a window-prior-based generative network for cross-modality CT synthesis. Instead of predicting the full dynamic range up front, Wing reformulates the regression target into multiple windowed representations. The core generator is built on the MedNeXt backbone, but we made a critical architectural shift. MedNeXt relies on large kernel depthwise convolutions to capture spatial context, but the computational cost scales cubically with kernel size, which quickly becomes prohibitive for 3D volumes. We replace those blocks with a gated inception structure. The input channels are split across 4 parallel branches, a standard 3D kernel, and 2 anisotropic kernels sized 3x9x3 and 3x1x9, plus an identity path. The anisotropic kernels are the key here. They expand the receptive field across the in-plane dimensions, while preserving tight mixing through the slice thickness. This captures fine structural details, without inducing the interslice blurring that large isotropic kernels often cause. To combine these branches, we don't just concatenate them. We pass the features through a lightweight pointwise convolution, apply a sigmoid activation to generate a gate map, and use element-wise modulation to adaptively reweight each branch. This gives the network a learnable, structure-aware mixture of multidirectional spatial features. The decoder then projects these features into 3 separate output channels, each corresponding to the lung, soft tissue, and bone window predictions. Generating the windows is only half the battle. You need to reconstruct the full-range CT without hard-clipping artifacts. We use a differentiable soft fusion operator. Instead of abrupt boundaries, we derive blending masks from the soft tissue window. The lower and upper bounds of the soft tissue channel naturally characterize the transition zones between windows. We apply a trapezoidal weighting function controlled by a parameter tau. When tau is low, the transitions are smooth and overlapping. When it's higher, the boundaries sharpen. This allows the network to learn seamless intensity, blending across anatomical regimes. But soft fusion alone leaves residual errors. The predicted windows never perfectly align with the ground truth distribution. To fix this, we route the windowed predictions through a fuse and refine transformer. The windows are downsampled into patch embeddings, processed by 2 transformer blocks to capture global dependencies and cross-window consistency, then upsampled back to full resolution. The transformer predicts a residual map, which we add directly to the softly fused CT. This residual refinement step is what recovers high-frequency structural details that the convolutional generator tends to smooth over. For training, we use a joint adversarial objective. Standard GAN discriminators only see the final output, but here we introduce a joint discriminator that conditions on both the windowed predictions and the fused synthetic CT simultaneously. This forces the generator to maintain realism at 2 levels, the individual anatomical windows and the integrated volume. The loss function combines L1 reconstruction loss for both the windows and the final CT, an LPIPS perceptual loss to preserve structural fidelity, and the adversarial loss weighted to balance sharpness against intensity accuracy. We empirically set the reconstruction and adversarial weight ratio to 1 to 3 to 4.1, prioritizing intensity accuracy while still pushing perceptual realism. We benchmarked Wing on the SynthRAD 2025 dataset, which contains paired MRI-to-CT and CBCT-to-CT volumes across head and neck, thoracic, and abdominal regions. We trained a single unified model across all 3 anatomies to test cross-domain generalization. The results are consistent. Wing outperforms state-of-the-art baselines like MedNeXt, Pix2Pix3D, and SwinUNETR across MAE, MSSSIM, PSNR, and dice similarity. But the real story is in the per-window error breakdown. Traditional models struggle hardest at the extremes of the intensity distribution. Wing shows significant gains, specifically in the lung and bone windows, directly addressing the long-tail regression problem. Visually, the synthetic CTs show sharper cortical boundaries, more accurate lung parenchyma texture, and fewer dose calculation critical artifacts. Wing demonstrates that CT synthesis doesn't need more complex architectures or external segmentation guidance. It needs better inductive priors that respect the physics of X-ray attenuation. By treating windowing as a fundamental learning target rather than a post-processing step, We get a compact, parameter-efficient model that handles multimodality and multi-anatomy synthesis in a single forward pass. The current implementation uses fixed radiological windows, which is clinically standard, but limits flexibility for unconventional acquisition protocols. Future work will focus on adaptive, data-driven window modeling to further improve generalization. If you're working on cross-modality synthesis or adaptive radiotherapy workflows, this window-prior approach is a highly effective way to stabilize intensity regression without sacrificing structural detail. Thanks for watching, and I'll see you in the next one.